So can you see the screen?
Yes, sir.
Okay, just wait a minute. Yeah, it seems somebody wants to join. Yes. Okay, so today we are starting with the new chapter. It's on fluid mechanics. Uh, we have mostly covered all the topics from thermodynamics part, and there are few things which are left now. I think somebody wants to join. Wait. Okay, so fluid mechanics. Fluid mechanics is that branch of science which deals with the behavior of fluids. So basically, we are interested in studying fluids. Fluids are either liquids or gases. Okay, that you should always remember. We have discussed about it earlier also, so you need not to worry much about it. Thus, this branch of science deals with static, kinematics, and dynamic aspects of fluids. So whatever we are going to study here in this fluid mechanics course, that is very very basic, and similar things you have studied already in thermodynamics. So it's not much in your course in on fluid mechanics actually. So study of fluids at rest is called fluid statics. Study of fluids in motion where pressure forces are not considered is called fluid kinematics. So in kinematics, we basically study about velocity, acceleration, etc. If the pressure forces are considered for fluids in motion, that branch of science is called fluid dynamics. So there are three things: statics, kinematics, and dynamics. Okay, and you should remember the definition of fluid. Fluid is something uh, which is which could either be liquid or gas, and when shear stress is applied on a fluid, its shape changes actually. Okay, and it can flow also under the action of the shear stress or shear force. So I think you have not studied about shear stress or shear force, so don't worry about that. We will discuss about that later on. Now when we talk about the various properties of the fluids, the first property is the density. See, density we have already studied in thermodynamics, and we have been using it many times. So density is nothing but the mass of the fluid per unit volume, and you know its unit is kg per meter cube. Okay, but here when we are talking about properties of fluid, we give it another name, that is actually mass density. Okay, so it's mass density, and it is written as rho. Somebody wants to join. So the density of water is, you know, is 1000 kgs per meter cube. So I think there is not much to make you understand about this. You already know about it. Okay. Uh, Now let us go to specific weight or weight density. Now this is important actually. Weight, specific weight or weight density. First of all, I will say that it is represented by a symbol small w, and it is defined as the ratio between the weight of a fluid to its volume. Okay, so it is the weight of the fluid to the volume of the fluid. So what is weight equal to? When we say weight is equal to mass of the fluid into acceleration due to gravity divided by the volume of the fluid. So we can say that small w is mass of the fluid into g divided by volume of the fluid. So it comes out to be that w is equal to rho times g. So it's rho times g. And because we know that the mass of the fluid divided by the volume of the fluid is given as the symbol density, or its density basically. And if you see it here, if we are calculating the value of the specific weight or weight density for water, its value will be 9.81 into 1000 Newton per meter cube. Why Newton per meter cube? It's quite simple to understand. Yes, once again, somebody wants to join. So weight density, we were talking about the weight density. So weight density of water is 9.81 into 10 raised to power 3 Newton per meter cube. I was telling you how do we calculate its unit. See, for density, the unit is kg per meter cubes, and for acceleration due to gravity, the unit is meter per second square. So if you see here, then this value kg meter per second square. Okay, this is mass and this is acceleration. Okay, so mass into acceleration is force. So force per meter cube. So basically, it becomes Newton per meter cube. So that is how we can calculate the value of the unit of specific weight. And this is very, very important that the specific weight of water is 9.81 into 1000. Specific volume, we have already studied about it. What is specific volume? It is denoted by small v, and it is the reciprocal of density. You know about it. Okay, it is volume per unit mass of the fluid, and you know its units are meters cube per kg. Now, yes, this is important here. Specific weight. Now, what is not specific weight, rather specific gravity. Now, let us go to the definition here. First of all, the symbol for specific gravity is capital S. Okay, so we are writing here specific gravity of liquids. What is specific gravity of liquid? It's the weight density or density of the fluid divided by weight density or density of the water. So, for example, if we have to calculate the specific gravity of any fluid, then it will be written as the weight density of the liquid divided by the weight density of the water, or the density of the liquid divided by density of the water. So its formula means its formula S will be equal to, you can say, rho for the particular liquid. I would say not fluid. I will write it as liquid here. Okay, just wait a minute. So it is density for the liquid divided by the density for the water, and we can also write it as it is specific weight for the liquid divided by the specific weight for the water, because you know that this specific weight is written as rho into g. So it is for the liquid, and here also we can write rho into l, rho into g for the water, and g is acceleration due to gravity, and that will cancel out, and we are left with density of the liquid divided by the density of the water. But if it is a gas, in case of gas, in the denominator we compare its weight density or density with respect to air actually. So if it is a gas as the fluid, so its specific gravity S will be given by the density of the gas divided by the density of the air, and it can also be written as specific weight of the gas divided by the specific weight of the air. And then once suppose we know the specific gravity of a particular liquid or gas, and we want to calculate its weight density, then weight density can be directly calculated as specific weight into weight density of the water. Okay, and the weight density of the water you already know is 1000 into 9.81, this much Newton per meter cube. So from here we can calculate the weight density of the liquid, and in a similar manner, if we want to calculate the density of the liquid, then we will multiply here the specific gravity with the density of the water actually. Okay, and similarly we can treat it for the gases also. Now there is one very important fluid here, which is mercury. So for Mercury, the specific gravity is 13.6. So it means Mercury is 13.6 times heavier than water. Okay. So the density of the mercury will be, you can say, 13.6 into 1000. So it will be 13,600 kgs per meter cube. And if we want to calculate the specific weight for mercury, and then its value will be equal to density of mercury into um, acceleration due to gravity. So it will be equal to 13600 into 9.81 Newton per meter cube. Okay, so now let us look at the numerical problem. This problem is calculate the specific weight. That means we want to calculate the small w, density means rho, and specific gravity means s, for 1 liter of a liquid which weighs 7 newtons. So this is the value of the weight. Okay, so what we can do is we can first of all calculate the volume. Volume of this liquid is given as 1 liter, and you should always remember that when we divide it by 1000, then we will get this value in meter cube. So it becomes, and this is given here also, 1 liter is equal to 1 by 1000 meter cube, or 1 liter is also equal to 1000 centimeter cube. So you have to remember this conversion. So the weight is given as 7 newton. Okay, so how to calculate the specific weight? See, once again, specific weight, small w, is given as uh, it is equal to weight per unit volume. If you calculate the density, then we use mass per unit volume, but so we call this as the mass density or density, and this W we call as the weight density, because we are considering the weight of the fluid here. This weight density is also called as specific weight. Okay, specific weight. So it's quite easy to understand. We are defining two terms. One is the weight density and other is the mass density. When we say mass density, then the mass is to be divided by the volume. When we call weight density or specific weight, we divide the weight by the volume. So you can see here specific weight, also known as the weight density. Okay, so this value is weight per unit volume. So this is the value of the weight in newtons, and this is the volume. So the answer comes out to be 7000 newton per meter cube. This is the weight density. Now let us calculate the density. So we have the relationship that weight density, see, W is equal to rho times G. Okay, this is the specific weight or the weight density, that is equal to mass density into acceleration due to gravity. So from here we can calculate the value of rho. Rho comes out to be W divided by G. So it is 7000 divided by 9.81. So answers comes out to be 713.5 kgs per meter cube. Now the next part is to calculate the specific gravity. Specific gravity is the density of the liquid divided by the density of the water. Okay, so you can see it here. Why we are taking density of the water? Because the liquid, it's mentioned here in the question. This is the volume of the liquid actually. So we can divide the density of the liquid by the density of the water, and the answers for the specific gravity, which is denoted as S, is equal to 0.7135. So any questions on this? I hope this must be clear to you. Now this is the next question, similar question. So let us see it once again. Calculate density means we want to calculate rho. We want to calculate specific weight, which is given as rho into G, and the weight. Weight means you can say uh, M into G. So that is the value of the weight of 1 liter of petrol of specific gravity 0.7. So this is the value of the specific gravity which is given to us. So first of all, we calculate the volume, which is given as 1 liter. We can convert it into centimeter cube by multiplying by 1000. Then we can convert it into meter cube, so it comes out to be 0.001 meter cubes. You should always remember that if it is 1 centimeter cube, you need to divide it by, because 1 meter is equal to 100 centimeter. So here we have the centimeter cube, so the value will be 1 into 10 raised to power minus 6 meter cubes. So now the specific gravity is given as zero point 0.7. So you know that S is equal to density of the liquid divided by the density of the water. So density of the liquid will be equal to S into rho W. So S is given as zero point 0.7 and the density of the water is 1000. So the answer will be coming out to be 700 kg per meter cube. Then we calculate the specific weight. So what is the value of specific weight? It is equal, specific weight is nothing but the weight density. Okay, it is weight density. So weight density is given by weight divided by the volume. So what is the unit, what is the formula for weight? It is equal to m into g divided by v. So it means it is m by v is rho, rho g. So weight density is rho g. So the density is already known to us, 700 into 9.81. So it comes out to be 6867 Newton per meter cube. Okay. So the next thing that is asked us to calculate is weight. So weight is m into g. So mass is not known to us, but using this particular equation, specific weight is given by weight per unit volume. Okay. So from here, the weight will be equal to, uh, you can see the equation here. This is the equation here. Okay. So specific weight W is equal to, small w is equal to capital W divided by V. So we know the value of the specific weight, we know the value of the volume, so only unknown is weight. So it can be calculated using this equation and it comes out to be 6.867 newtons. Okay, so now let us proceed further. uh, the next is the viscosity. This also you must have studied in your uh, uh, 11th or 12th class. So what is viscosity? Viscosity is defined as the property of a fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of the fluid. Okay, when two layers of a fluid are at a distance dy apart, move over one another at different velocities, say u and u plus du. Now see this diagram actually. Now what we have shown here is, this is a solid surface, this is a solid surface. Okay, now what happens, suppose some fluid is flowing over it. This is a fluid having a velocity, let us say u. So what will happen? The velocity which of the layer which will be sticking to this solid surface, its velocity will be zero. Okay, this velocity will be zero. And the velocity in the y direction, this is the, you can say this is the x direction and this is the y direction. So in the y direction, you will see that initially the velocity of the layer which is sticking to the solid surface is zero, then it keeps on increasing like this. Okay, so this is the velocity profile. What is this? This is the velocity profile. Velocity profile means, if I take this particular location at a distance y from the surface, then this is the velocity u. If I take this distance, this value, say let us say it is y2, then this is the velocity. And here the velocity I am considering is u plus du, and before, just below it, in the layer which is below the top layer, the velocity is u. So we are saying that these two layers are very near to each other, and the distance between these two layers is dy only. Okay, so, and you know that this variation in velocity is because of the viscosity, which is the property of the fluid. So it is the viscosity which causes or offers resistance to the uh, motion of the one layer of the fluid over the another layer of the fluid. So the viscosity together with relative velocity causes a shear stress acting between the fluid layers. So I told you we will be talking about the shear stress actually. Okay. So shear stress when one layer of the fluid which is moving faster, like this layer, this is moving faster because its velocity is u plus du, and this layer, this is a little bit slower. Okay, this is a slower layer. So the upper layer will be moving parallel to the lower layer, and it will be causing stress or shear stress to act between these two layers, and this shear stress is responsible for the friction between the two layers actually. Suppose there are two layers, if they are moving parallel to each other with the same velocity u, then will there be any friction between these two layers? No, because all the points when the two fluid layers are moving with respect to each other, they are at the same velocity, so there won't be any restriction sort of thing, or there won't be any what you call, there won't be any friction actually, because they are moving at the same speed. Okay, so the top layer causes a shear stress on the adjacent lower layer, while the lower layer causes a shear stress on the adjacent top layer. This shear stress is proportional to the rate of change of velocity with respect to y, and it is denoted by a symbol tau. Tau is basically shear stress. So we say that this tau is proportional to du by dy, and this du by dy is nothing but velocity gradient. It is velocity gradient, means the velocity between two parallel layers is different, it's varying actually. So we are focusing on any two layers like this layer has the velocity u plus du, and a layer just below it which is at a distance, you can say dy, the velocity here is u, and the difference in the velocity between these two layers is actually du, and the distance between these two layers is dy. So we say mathematically tau, this tau is shear stress. What is tau? It is shear stress. Okay, shear stress is proportional to du by dy, and when we remove this proportionality sign from this equation, we get this particular equation: tau is equal to mu du by dy, and this mu is actually known as the constant of proportionality, is known as viscosity, or sometimes we call it as dynamic viscosity. Okay, dynamic viscosity. So I hope this is clear to you. Now what we will do, we will find out what is the unit of the viscosity. You can see here, this is the shear stress. Tau is equal to mu du by dy, and you can see here this mu is called the constant of proportionality. It is known as the coefficient of dynamic viscosity, or only viscosity, or sometimes we also call it as absolute viscosity. Okay, absolute viscosity is another name, and viscosity we can also call it as coefficient of viscosity. Okay, we can also call it as dynamic viscosity. Okay, so it has four names: absolute viscosity, viscosity, coefficient of viscosity, and dynamic viscosity. And this term du by dy, what does it represents? It represents the rate of shear strain. It is known as the rate of shear strain, or rate of shear deformation, or velocity gradient. I have told you this term. So once again, it has also two other names: shear deformation and rate of shear strain. So these are the other names. So now the mu is given as tau divided by du by dy. Now what is stress? Stress, I think you must have studied earlier also. It has the same units as that of the pressure. Okay, so mu is equal to tau divided by du by dy. Okay, and this shear stress, it has the units of pressure, and the pressure units are Newton per meter square. U, if you take U has the units meter per second, whereas the Y has the units of meter. So meter and meter cancels out. We are left with Newton second per meter square. And if you remember exactly that Newton per meter square second, this value of Newton per meter square is Pascal and second. So the units of viscosity are Pascal second. Okay. Uh, Now let me tell you once again something more about it. Yeah, this is the kinematic viscosity. I will introduce one more slide here to tell you something more about it. So I said that mu is equal to tau du by dy, and I said that the unit comes out to be Newton per meter square second, which is nothing but Pascal second. Now it has another, so this is basically SI unit. What is this? This is SI unit. Now if you go for CGS system, the unit of viscosity is given as poise. Okay, and uh, 10 poise is equal to 1 Pascal second. So it means if I am given with 1 poise, that would be equal to 0.1 Pascal second. Now what is this poise actually? Okay, so sometimes no, because I am saying it is the CGS system. So CGS means centimeter gram second system. So we will have to take the values in centimeter gram and second, so that we can find out what is poise actually. Uh, Poise is okay. Let us see. Now I am saying that tau is equal to mu is equal to tau du by dy, and this is Newton per meter square. So because I am also not remembering it, so I will explain you based on my knowledge. So Newton we represent as kg meter per second square actually. Okay, it is kg meter per second square, and per meter square. Okay, so I'm talking about the units of tau. So if I have to use it, find out the unit of viscosity in CGS units. So what I will do, I will take mass into acceleration divided by area, because tau is what? It is equal to force per unit area. Tau has this particular units, and force is Newton, area is meter square. If I write Newton is force, which is equal to mass into acceleration divided by area. Okay, so just I am trying to decode what is poise. So now what I will do, I will write the units of tau in CGS system. So mass, I will take the mass in grams. Then acceleration is if in SI system of units I write meter per second square, but here I will write centimeter per second square. Okay, area I will write in centimeter square. Okay, then below tau we have du by dy, and du means meter per second. So in CGS system it will be centimeter per second, and divided by dy, once again we have centimeter here. So centimeter cancels out, and then this centimeter and this centimeter cancels out, and we are left with gram uh, per second square per centimeter. So this is basically, you can say, poise. Okay, this is poise. So now let us see how we can convert it in SI system of units. So let us try to understand it. So we are given with, I will keep utilize this particular space here. So we have gram per second square centimeter. So if I have to convert gram into kilograms, I will have to divide by 1000. So I will divide here by 1000. So what I will get, I am now able to convert this gram into kilograms, and I have this centimeter here. So for converting centimeter, I have to divide by 100. So this 100 will come here. Okay, so it will be second square, and here we will have meter. Okay, so this becomes, you can see 0.1 kg second square and meter. But I said that the unit of viscosity is Newton second per meter square. So let us see it here. It is equal to 0.1 kg. I can multiply by meter. I can divide by meter into, I can write 1 divided by second square meter. So it will become zero point 0.1. Now you just focus here. Just a minute. This kg and meter per second square. Now kg is mass, meter per second square is acceleration. So it becomes Newton. Okay, and uh, in when we are dividing here, it becomes meter square. Yes, but there is second also. Yes, there is some mistake here. We would were to cancel this second also, so it will be second only. Okay, so here we have this second. Okay, so this will, there won't only a single second here, single second. So what we do, we also multiply here by second and divide by second. So naturally now you can see it here in the denominator. uh, Here you will have to multiply by one more second. So you can see here, this is the SI unit, which is equal. So if you take 1 poise, this is 1 poise, it becomes out to be 0.1 Newton or Pascal second. But you need not to remember all these uh, what you call change of the units. You should always remember this only, these values. Okay, so don't worry. 10 poise is equal to 1 Pascal second, or 1 poise is equal to 0.1 Pascal second. Okay, that is what you need to remember. Now let us go to the next definition. It is about kinematic viscosity. Kinematic viscosity is defined as the ratio between the dynamic viscosity and the density. So mu is equal to, sorry, it is denoted as nu. So it's not written perfectly, all right. It should be written like this. So nu is equal to mu divided by rho. It is kinematic viscosity, and it has two units. One is, if you see here, dynamic viscosity, we already know the units. The dynamic viscosity units are Pascal second. Density has the units kg per meter cubes. Okay, so finally when you will cancel it out, you will find that the units for kinematic viscosity is meter square per second or meter per square per second. Okay, if you want to write it in CGS system of units, it will be centimeter square per second. And there are smaller units for what you call this, the name of this centimeter square per second is actually stroke. So one stroke is equal to 1 centimeter square per second. So when we want to convert one stroke into the SI system of units, we will have to divide it by 10 raised to power 4. So it will be equal to 10 raised to power 4 meter square per second. So centi-stroke is equal to 1 by 100 stroke, and one stroke will be equal to 10 raised to power minus 4 meter square per second. So it's once again units which are playing a major role here. Now, what is Newton's law of viscosity? We have already discussed about it when we were talking about the viscosity. So it says that the shear stress on a fluid element layer is directly proportional to the rate of shear strain. We talked about this diagram where we were talking about the variation of the velocity. Okay, this is the velocity here. This is u. This is u plus du. Okay, and this is equal to dy. This diagram I showed you earlier also. So I said that this tau is proportional to du by dy, and when we remove this proportionality sign, we get this particular equation. This particular equation. So this constant of proportionality, you know, it is coefficient of viscosity. So then this is very important line here. Fluids which obey the above relation are known as Newtonian fluids, and the fluids which do not obey the above relation are called non-Newtonian fluids. So what is Newtonian fluid? For example, water. It is a Newtonian fluid. You talk about air. You talk about kerosene. Okay, these are the some of the fluids which obey the Newton's law of viscosity. That the shear stress. And what is tau? Tau is shear stress. Okay, so it is Newton's law of viscosity. Now let us talk about the types of the fluids. Now, what are the various types of the fluid? The first fluid is ideal fluid. The second is the real fluid. Third one is the Newtonian fluid. The fourth one is the non-Newtonian, and the fifth one is the ideal plastic fluid. Now, what is a ideal fluid? A ideal fluid is one which is incompressible and have no viscosity, is known as an ideal fluid. Ideal fluid is only an imaginary fluid, as all fluids which exist have some viscosity. So basically, when we say a fluid which does not have any viscosity, means when the layers of this fluid will move over one another, there won't be any frictional force, there won't be any resistance to the motion, because viscosity actually talks about the resistance to the motion. So there is no viscosity, and hence when there is no viscosity, so there won't be any velocity gradient. So the value of the velocity gradient, yeah. So this is the ideal fluid. Okay, so the velocity, because mu will be equal to, there won't be any velocity gradient, so mu will be equal to, if you would like to calculate the value of mu, is equal to tau divided by du by dy. So the value of the viscosity will be infinite. Okay, this value is 0 here. Then we talk about the real fluid. A fluid which possesses viscosity is known as the real fluid. All the fluids in actual practice are real fluids. So you can draw a real fluid. All these are basically real fluids. They are the real fluids. Okay. Then comes the Newtonian fluid. I have already told you, a real fluid in which the shear stress is directly proportional to the rate of shear strain or velocity gradient is known as the Newtonian fluid. Okay. So I told you the examples: water, kerosene or air. They are the Newtonian fluids. Then non-Newtonian fluids which do not obey the Newton's law of viscosity. A real fluid in which the shear stress is not proportional to the rate of shear strain or velocity gradient is known as non-Newtonian fluid. Means this tau is not equal to mu du by dy. If such a relationship is existing, then we will say it is a non-Newtonian fluid. And an ideal plastic fluid, in case of ideal plastic fluid, as you can see, when we apply a particular value of the shear stress, then you cannot find any velocity gradient. The value of the velocity gradient remains 0, and then suddenly means there is a linear relationship between the shear stress and the velocity gradient. Such a fluid is known as the ideal plastic. 1 minute, I in the first case when I was talking about the ideal fluid, I think I explained you wrongly here. Now let us try to understand this ideal fluid here. First of all, the density of an ideal fluid is, means it is incompressible. So that means the density is constant. One thing, and the second is the viscosity. The viscosity value is 0, because you can see here it's a straight line. It is shown by a straight line here. Okay, so The value of shear stress in this particular case is 0. So if I say mu is equal to tau uh, divided by du by dy. Okay. So first of all, forget about du by dy. You see this value. There is no shear stress. So the value of viscosity in this case comes out to be 0. So basically, a ideal fluid is 1, in which case the value of viscosity is 0. Whereas in case of Newtonian fluid, if you see here, this is a slope. Okay, what is this value? Actually, this is actually showing the value of mu. So slope is mu actually. Why mu? Because you can see here, it is tau divided by du by dy. So that is why this sort of this slope will be representing the viscosity of the fluid. So let us talk a little bit about pressure also. So basically, these are very simple definitions here. You can go through them. Now I'm going to the next chapter. It is on pressure and its measurement. So don't worry, it's all you have studied in thermodynamics part also. When we say pressure, okay, we know that we defined pressure in thermodynamics also. Pressure is normal component of the force per unit area. So here also it is defined the same way. Pressure is equal to force per unit area. So it is normal component of force. Okay, normal component of force. It's written here also in normal direction. So force will be given by pressure into area, and the pressure units are, forget about this unit. Don't use it. It is MK system of units. Go for this unit, Newton per meter square pressure. I have already told you, and Newton per meter square is Pascal. Okay, this is the SI system of units. So Newton per meter is known as the Pascal and represented by PA. Kilopascal, we already know it is equal to 1000 Newton per meter square. Bar, you know, is 100 kilopascal, 10 raised to power 5 Newton meter square. Pascal's law, very simple. It states that the pressure. Now, when we are talking about fluid mechanics, we say pressure or intensity of the pressure. They are one and the same thing. Okay. At a point in a static fluid is equal in all directions. So that is the Pascal's law. So if I am talking about the fluid here, there is some fluid here. For example, this is a container. So if I say this is the particular point, so the pressure in all directions is equal. So P. Okay, so all the values are equal at a particular point, and there is no proof. We are not going for its proof actually. So if we are considering some small element here in the fluid, okay, like shown here, it is the pressure in the x direction, it is the pressure in the y direction, it is the pressure in the z direction, then we can always say that px is equal to py is equal to pz, and no proof is required for it. So next is the pressure variation in a fluid at rest. Okay, so once again I will say that this is known as the hydrostatic law. It states that the pressure at any point in a fluid at rest is obtained by hydrostatic law, which states that the rate of increase of pressure in a vertically downward direction must be equal to the specific weight of the fluid at that particular point. So don't worry once again about it. I will tell you, for example, if this is a container here, and here the atmospheric pressure is acting, okay, and I want to measure the pressure at this particular point, which is at a distance h from the, this is the free surface of liquid. Okay, then I will say, and let us say this is the density of the liquid is rho, and its weight density is w. You know that weight density is given by rho into g. Okay, so then I can say that this pressure, because of the head of the liquid at over this particular position, is h. So this h is the head, which is head of the fluid, which is acting on this particular point, and it is making the pressure to increase at this particular location. So I will say that uh, pressure at, if I call this point as a, pressure at point a is equal to rho g h. Okay, this is, but this pressure is only you can say gauge pressure. Okay, and if I want to calculate the total pressure here at point number A, that will be equal to P atmospheric plus rho g h. And this we also studied when we were talking about the pressure in the first chapter in the uh, thermodynamics. So you can see it here. The derivation is given here. I am not interested in the derivation part. And finally, you can see it here. This is the hydrostatic law. Del P by del Z is equal to W, or I can say, you can see it here, uh, this this value. dP is equal to rho g dz. Now this Z, actually I have used H whereas they are using Z. So if I say that once again to explain you so that you don't get confused, this is the point A, and from the free surface of the liquid it is at a distance Z from the free surface. This is the free surface. Okay, and we want to calculate pressure due to this head of the liquid. Now this Z is head of liquid, head of liquid. Okay, so because of this head of liquid, the pressure is actually given by this formula. P is equal to rho g z. I have told you earlier that P is equal to rho g h. Because I used h there in the diagram, they are using z instead of h, so P is equal to rho g z. So this is actually known as hydrostatic law. And that means if pressure for a particular fluid is given to me, I can convert that into pressure head actually. Okay, this Z is nothing but head of the liquid. So focus it here. Z is pressure head. It is pressure head, and its unit is meters. So just try to see this equation also. This P is equal to rho g z. You know rho is kg per meter cube into meter per second square into meter here. So this value is, it is Newton. Okay, and this cancels out. So we are left with Newton per meter square. So it gives us the units of pressure, which is Newton per meter square. And once again, this Z is known as pressure head. And if the pressure of a fluid is given to me, then I can always calculate its head. Okay, by rho g, as P divided by rho g. And we have already studied about absolute and the gauge pressure, vacuum pressure also. This diagram I have already explained you. If you want to understand it, you can once again go to the uh, first lecture of thermodynamics, and you can, where I have explained it completely. Only one thing I would like to tell you here, I think this I have already told you. 760 millimeter of mercury column is equal to 1 atmosphere. I told you when I was teaching you basic mechanical engineering, this thermodynamics course also. And it is equivalent to 10.33 meter of water column. Okay, we said that 760 millimeter of mercury column is equal to 1 atmosphere. We can also call it as the 10.33 meter of the water column, that is equal to the 1 atmosphere. Okay, so this is what I wanted to teach you, because now it is today's time is over. It's 2:59 by my watch, rather 3 now. Okay, so I will end my lecture here. So it's all simple things, only basic definition. You can, I have already sent you the notes, so you can go through those notes also and read it from there. If you have any questions, you can ask me.